Dear students, today we are going to talk about continuous function. So it's the last one part of the so-called chapter 1. So you have read about continuity when you are talking about functions of one variable. Now here we are going to talk about functions of n variables. So continuity on a very rough scale or a rough way to define continuity means a small change in x would record a small change in y. So if you see a small change in the function values, there is a corresponding small change in x to which it corresponds. So um, so just to colloquially remember about continuity, a small change in x gives a small change in y. So when you put it in the epsilon delta definition, it says that give me an epsilon no matter how small, I can always find a delta which depends on the choice of epsilon, such that norm of fx minus a is less than epsilon whenever x minus norm of x minus a is less than delta. So this is what is the meaning of continuity at a point A. Of course, if it is continuous at all the points, then it is continuous over the whole Rn. Now, what's important is the following: is that what does it mean? It means then if you give me very small epsilon greater than 0, no matter how small, I can always find a delta such that whenever x is in the open ball of radius delta centered at A, f of x is in the open ball of radius epsilon centered at Fa. That is the meaning. So this is the definition, which this is again, if you look at it, this essentially means that whenever x tends to A, f of x tends to Fa. That's it. So there is a sequential definition also that a function is continuous at A if and only if when for any sequence xn such that xn going to A, f of xn goes to f of A. It simply says that the idea of limit and the sequence of and sequence is interchangeable. Means limit of f of xn is f of limit of xn. That's the idea. Now in some cases we have to use vector valued functions, that is a function which takes an element in x in Rn and moves it to an element in Rm. Well, Rm, that m need not be just 1, it could be 2, 3, whatever. But any function like that can be viewed through its component function. F of x from Rn is mapped to a vector in Rm. So f of x is a vector in Rm. So each of the components of that vector depends on the x. You change the x of x, capital Fx would represent a different vector in Rm. So each of the individual components are actually functions of x, which are of course functions from Rn to R, and we have known about Rn to R. So a function capital F from Rn to Rm is continuous if and only if all the component functions f1 dot 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 fmx is continuous. So I leave it to you to write down the epsilon delta definition. So I don't think this is much of a here there is a small mistake in the writing. So here it should not be norm here, it should be mod here, because f is in Rm. So essentially I have given you the definition from Rn to Rm essentially. Because I have put a mod, instead of mod I should have put an absolute value. So because this is in R, so please pardon me for this. So it will be mod of an absolute value of fx minus fa less than epsilon. So fx minus fa less than epsilon means fa is in the epsilon neighborhood, fx is in the epsilon neighborhood of fa on the real line. That's it. So now once I know about a continuous function f from Rn to Rm, and you know how to write down the epsilon delta definition now, just you put m here and everything remains the same, but this would be a norm in Rm and this would be a norm in Rn. So there is an interesting characterization, a very important characterization which some people call a topological characterization. In fact, the most general way to define continuous function is this at the end, but which can be proved as a theorem in case of functions from Rn to Rm or functions from Rn to R. A function capital F from Rn to Rm is a continuous function if and only if you give me any open set U in Rm, F inverse U, the inverse image, is an open set in Rn. Please understand, if you even take a single point x in Rn, x in Rm, F inverse x is in general a set. The inverse mapping is not always a point mapping unless there is a bijection. And when bijection would happen when n is equal to m. Bijection would happen when instead of m here I should have n. Now, so for a set U, F inverse U is obviously a set. It's called the inverse image of the set U. So what it says that if you take any set U in Rm, then F inverse U, the inverse image of U, would be in an open set in Rn. So what it tells you that for any open set that you take in Rm, open set, please understand, not any set. So F is continuous if and only for any open set that I choose in Rm, the inverse image of that open set is going to be an open set in Rn. So repeat this self to you. If you don't think that you want to follow the proof, you may not follow it, but it's an instructive proof, very simple though. But I think you can actually follow it and do it. It's a nice proof, I would say. Proof is interesting. The proof is based on that of Corner, and so I just want to give you the details. The proof is based on the book by Corner, which I have mentioned in the in the notes. Here also at the end I will put the reference. So, but before that, when I end the full talk, I'll obviously put the reference. But till then, I just want to let you know that this approach is based on T.W. Corner's book, Companion to Analysis, one of my favorites, which I had shown you earlier that this would be one of the books I'll consult quite frequently. So let us first start with the fact that capital F is continuous and U is open. Okay, and open in Rm. Now what I want to prove is that F inverse U should be open in Rm. So now let X be an element of F inverse U. Okay. So I have to prove that whatever X you take in F inverse U, X must be an interior point of F inverse U. So if X is in F inverse U is in the inverse image, then F of X, the image of F of X must be an element of U. The image of X, which is capital F of X, must be in U. Since U itself is an open set and F of X is in U, so there must be a ball, say an epsilon, ball of radius epsilon, which will be completely contained in U. Now again I know that F is continuous. So given this epsilon, which I already have here from this epsilon, I can always find a delta such that this norm of Fy minus Fx must be strictly less than delta whenever norm of y minus x is less than delta by definition of continuity. So what does this say? Whenever y is in the open ball of radius delta centered at x, we have f of y in the open ball of radius epsilon centered at f of x. Now this thing, fx epsilon, b of fx epsilon, the open ball of radius epsilon centered at fx, is a subset of u. So f of y hence is a subset of is an element of u. So y is element of f inverse u. So what did I prove? I have proved that given this x, I have found a delta such that the open ball of radius delta with center x is completely contained in f inverse u. Since x was arbitrarily chosen, which means any point in F inverse u is an interior point, and hence F inverse u is open. Conversely, let us assume that F inverse u is open in Rn. Whenever you have u open in Rm, and I have to prove the continuity of F. Now consider any x and take any epsilon greater than 0 no matter how small. I have to prove that capital F is continuous at x. So it is continuous over Rn because x is arbitrarily chosen. As the ball of radius epsilon centered at Fx is open because open ball is open. So from our assumption, F inverse of the ball, inverse image of the ball is also open. But one has to observe that f of x is in the ball itself because Fx is the center of the ball. So it is inside the ball, open ball. So x is in the inverse image of the ball. Okay. Hence, as if the inverse image, F inverse of B Fx epsilon is open, there must exist a delta such that a ball, open ball of radius delta centered at x must be contained in the inverse image of the open ball Bfx epsilon. Which means whenever I choose a y in this Bx delta, whenever I choose a y here, y at the same time belongs to F inverse of Bfx epsilon, which means f of y belongs to Bfx of epsilon, which can be written as the following, that norm of fi minus fx is strictly less than epsilon by this fact, the definition, whenever y belongs to this, y belongs to Bx delta, that is y belongs to, y satisfies this definition, norm y minus x strictly less than delta. And because this is, as I told you, x was arbitrary, we have proved it. So thank you very much. With the next part, we are coming up on issues of optimization, rather maximization, minimization, a very fundamental theorem called Weierstrass theorem, which you possibly have read in real analysis, but this is done for the higher dimensions. Thank you very much.